Sluishuis is a symbolic building representing the modern residential expansion of Amsterdam, Netherlands. It takes the form of a gateway extending toward the waterfront in Iceberg, a district comprised of a new residential model based on floating buildings. Built with a massive opening over water and founded on soft subsoil, the building's irregular shape posed numerous engineering challenges. Sluishuis was constructed over water while retaining Amsterdam's characteristics of underwater soil, using a system that distributes the building load broadly like a matrix. To achieve this, the foundation consisted of 714 precast concrete piles, each 15 to 17 meters long, and 99 steel pipe piles measuring 55 to 57 meters long. Since the entire cantilever portion of the building acts as a single bending member, the substructure and foundation that support it also have to be equipped with a specialized structure system. This foundation was divided into 3 zones: a compression zone bearing high compressive forces, a matrix zone distributing loads broadly, and a tension zone designed to resist minor tensile forces. Construction of sluices began with the installation of approximately 800 piles underwater. The piles were densely arranged in the L-shaped, lower portion of the structure, which was designed to draw in water. The shape of the L was first marked, and lead piles for the future inner cofferdam were installed to delineate the working area and ensure precise pile positioning underwater. The foundation required large and heavy structural components, and the site's waterfront location were leveraged by transporting large prefabricated materials and modules via barge. The precast piles were manufactured at a plant and brought to the site, where they were erected vertically using a barge crane and installed with vertical pile drivers. In the tension zone, the required strength was 10,000 kN. The total of 56 precast reinforced concrete piles, each 400 mm², were installed into the second sand layer, located at a depth of 21 to 23 meters, where they resisted tensile forces through skin friction with the soil. These piles were spaced at 1.4 meter center-to-center intervals, arranged in 14 columns by 4 rows. Another area where precast piles were installed, the matrix zone, acts like a cushioning layer much like a matrix, dispersing the building's load widely. This approach, which avoids reliance on firm soil strata, prevents settlement even on soft ground by distributing the load. The piles were arranged to match Sluishuis' load transmission mechanism. For example, 4 piles beneath interior columns, 2 piles beneath exterior columns, and specific placement between long spans. The compression zone supports the massive compressive forces and moments transferred from the cantilever strut walls. Located at both ends of the L-shaped basement, this zone was designed to support a total required load of 285,000 kN, using 48 steel pipe piles. Each pipe pile had an outer diameter of 990 mm and an inner diameter of 864 mm, and was filled with reinforced concrete after installation to sustain concentrated loads of 6,000 to 10,000 kN. To ensure stronger support, these piles were driven into the third sand layer at depth of net -59.5 meter to -62.5 meter. They were arranged at 2.1 meter horizontal spacing and 1.5 meter vertical spacing, with 12 columns by 4 rows per compression zone. To enlarge the contact area between the structure and the soil, and to better support the inclined loads from the strut walls. These piles were installed at a 20:1 inclination. The steel pipe piles were assembled with threaded tips and installed using rotary drilling equipment. This method was adopted due to the impracticality of using conventional pile driving techniques at such depth. Once the piles reached their design depth, Reinforcing cages were inserted, and concrete was ported to create high-performance pile with maximized structure capacity. After the piles were installed by barge, the construction of the underwater basement of Sluishuis required the creation of the dry work environment, which was achieved through the installation of cofferdams. An inner cofferdam was installed to secure the space where the basement would be built, and an outer cofferdam was placed along the water's edge to secure a working area between the inner and outer cofferdams, where construction equipment and temporary structures required for the Sluishuis construction process could be placed. Temporary land was reclaimed. The cofferdam system for Sluishuis used a method where sheet piles were slowly pressed into the ground using hydraulic pressure. The installed piles were Z-shaped sheet piles made of steel plates 25 to 30 meters in length and 6 to 12 millimeters thick. These sheet piles were installed based on the positions of previously placed lead piles, and as each pile was placed, it was interlocked with adjacent piles to gradually form the full enclosure. While installing the cofferdam from the barge, steel beams were simultaneously installed across the inner cofferdam using another barge-mounted crane to create a stable lateral bracing structure. Around the final stages of the inner cofferdam installation, land reclamation began between the inner and outer cofferdam to perform a temporary work platform. Some parts of the outer cofferdam were installed, and soil was backfilled from the barge between them and the inner cofferdam. This established a work site for the Sluishuis construction, allowing equipment to be moved into place and basement work to begin. The first task in the basement construction was to remove the sludge layer underwater and construct an earth platform and foundation capable of supporting the structural load. The ground level of Sluishuis is now 2.2 meters, and the two basement levels are a total of 6.59 meters high, which places the second basement level at the seafloor level in this location with a water depth of 4 meters. Although the structure was supported by piles, the sludge layer was unsuitable for placing concrete elements, so 2.2 meters of soil were removed inside the inner cofferdam, matching the thickness of the compression zone footings. Then, sand was placed to form a new base at the appropriate elevations for each foundation. Sluishuis features a structure system with an overwhelming number of precast concrete piles that distribute load widely. These piles were not placed at regular intervals but were specifically positioned to align with load-bearing points, making separate spread footings unnecessary. The precast piles were encased in concrete up to the development length to protect them during pile driving and secured the increased length of reinforcement. Heading work was performed to expose the rebar to the required increased length. After that, reinforcement for the mess slab, which also functions as a foundation at the second basement level, was placed and the slab was poured. However, the compression zone was different from other areas. It was a location where large and complex loads concentrated, transferred through inclined cantilever strut walls, then through large basement shear walls, and finally to the compression piles. Therefore, a footing was required to distribute the load and ensure structural integration. During the initial sludge remover, no sand bedding was added in these areas. Instead, reinforced concrete was poured inside the steel pipe piles, and the increased rebar extending above was rigidly connected to a 2.2 meter thick massive footing built atop the piles. This structure served as both the foundation connection and the second basement level floor. After the second basement floor was completed, the first basement and ground floor slabs were constructed using a distinctive semi-precast method. All slabs in Sluishuis are flat slab systems, and an efficient method was needed to construct the wide L-shaped slab areas. The system adopted was the Dutch spread-plat system, which uses thin factory-produced reinforced concrete panels that function both as bottom reinforcement and permanent formwork. These spread-plat panels were placed spanning columns and external walls, and the load was supported by temporary props. On top of the spread-plat, Upper reinforcement, including grid-form horizontal reverse and stirrups, was added according to the flat slab structure. These were connected to rebars projecting from columns and walls. The most prominent structural element in the basement of Sluishuis is the massive shear wall placed atop the compression footing. This wall serves as a starting point for the above-ground cantilever strut walls of Sluishuis. It had to withstand complex inclined compressive forces and moments, effectively transferring them to the compression footings and piles below. Once the foundation slab of basement level 2 was cast, reinforcement was placed for the shear wall by the geometry of the strut above. 18.6 meters in length, approximately 6.5 meters in height, and 1 meter in thickness. Sluishuis adopted a reinforcement strategy in which all steel components were prefabricated at the supplier's factory and then assembled on site. The first reinforcement to be placed were 6.5 meter long vertical rebars, which matched the full height of the wall. These were not left with the walls from the footing, but were placed immediately after the footing was cast, ensuring continuous integration between the footing and wall reinforcement. Following the placement of the vertical rebars, tie bars were slid down around them from top to bottom. With this in place, the horizontal rebars were then installed. At both ends of the wall, U-shaped rebars were used to tie the outermost horizontal rebars, providing strong lateral confinement. Another set of U-shaped rebars were installed at the top of the wall, tied to the vertical rebars to ensure vertical confinement. After reinforcement work was completed up to the level of the strut wall, formwork modules were installed on each floor, and the entire wall spanning multiple levels was cast monolithically to maintain continuity with the compression zone wall. After the basement works were completed, the space between the basement structure and the inner cofferdam was backfilled, and the inner cofferdam was dismantled to create the above-ground construction area. At the locations where the cantilever walls would be built, temporary piles were installed to support the falsework system for the cantilevers. These temporary piles were positioned so that their heads aligned with the ground level of Sluishuis and were connected to temporary reinforced concrete beams designed to resist the concentrated loads from the cantilever falsework and scaffolding. The concrete beams were arranged in offset, L-shaped patterns at 5.2 meter intervals, and diagonal beams are used to tie them together into one cohesive temporary structure system. To achieve this, each floor was constructed starting from the core zone, extending transversely toward the cantilever side. As construction progressed upward, the length of the cantilever increased by 5.2 meters per floor. However, the time allotted for wet joint bonding between floors, particularly between the cantilever strut walls, which are structurally critical, was limited. Therefore, the construction process was carefully sequenced to ensure that while a cantilever strut wall of one floor was being poured, the stair terrace and core section of the next floor was already under construction, and the cantilever zone of that same floor was also beginning to be built. This allowed for a consistent two-section buffer to be maintained between each cantilever wall pour, ensuring that structural integration through wet joints could occur within the required time frame. By defining precise construction duration and section intervals in advance, multiple floors could be constructed in a simultaneous and continuous sequence, achieving the level of structural monolithicity required for such a complex cantilevered building. Due to its unconventional geometry, Sluishuis adopted a method of dividing each floor into sections and expanding horizontally to ensure stability throughout the building process. Construction of the superstructure was carried out in blocks: floor G24, floor 5-8, and floor 9-10, each constructed using a similar strategy. In floors G24, the stair terrace sections were long, the cantilever sections were short, and the two wings were constructed independently. Construction began with the shear wall at the core located at the corner, where the stair terrace and the cantilever sections meet. This core area not only vertically connected the structure, but was also positioned near the compression zone foundation. which could handle high loads, making it advantageous to begin from this area. Once the core zone was established, transverse shear walls and twin shear walls within the section were constructed sequentially. After that, table formwork modules were placed between the shear walls and the slab of the section was cast. Because the cantilever portions on these floors were still short and the terrace joints were long, structural balance could be maintained even when both were constructed simultaneously. Furthermore, since the cantilever portion could not act structurally until its floor was completed, it was deliberately built last, so that the structural load would not act prematurely on the partially completed cantilever. Looking in more detail at how each floor was constructed, the apartments were organized along corridors placed between twin shear walls, with transverse shear walls spaced at 5.2 meter intervals to divide individual rooms. 3 such room units, approximately 15.6 meters wide, were treated as a single section for construction. In each section, the first step was to install and pour the transverse shear walls. After this, to cast the schematic table formwork system, which integrates table formed props, was installed between the shear walls. Then, the reinforcement for the flat slab, arranged in a grade of straight rebars, was placed over the entire section width, and the concrete was cast. This process was repeated section by section to complete each floor in a sequential construction method. The construction of the cantilever strut walls involved a far more complex process compared to other structural elements. Since the cantilever strut wall could not act structurally during construction, it required a temporary support system to bear its loads. A grid of temporary concrete beams was installed in the working area beneath the cantilever walls, upon which the modular quick-stage scaffolding system and the top 50 modular formwork were assembled. The scaffolding, made up of specially inclined frames and high-strength components, followed the geometry of the cantilever in a stepped terrace-like formation. These supports were anchored to the previous cast lower strut wall, securing them in place. Once the shoring system was set and plight was laid, the first components installed were several horizontal anchors and stud rails. The stud rails were used to resist localized shear stress resisting from vertical forces, where stirrup alone would have been insufficient. The anchors fixed to the plywood served to support initial horizontal rebars, which were not the primary reinforcement but acted as a base for vertical rebar placement. Because of the wall's inclination, fixtures were needed to stabilize the rebar during placement. The main vertical reinforcement, which is designed to resist axial compression and bending, was tied to these horizontal rebars with wire. Once the vertical rebars were set, tie bars across the thickness of the strut were placed and tied to the vertical rebars to prevent spreading and to enhance lateral confinement. Then, the lower layer of horizontal reinforcement was placed, with 2 bars inserted between each tie bar. This was followed by mid-level horizontal reinforcement, mid-height vertical rebars, and then top horizontal reinforcement within the upper tie bars. Subsequently, U-shaped rebars were installed at the ends of the cantilever's horizontal reinforcement and tied in place, creating lateral confinement across the entire width of the cantilever strut. These horizontal bars not only resist bending the 18.6 meter span, but also acted as longitudinal rebars along the sloped shear wall geometry, integrating with tie bars to confine the entire concrete section. Finally, additional vertical rebars were placed at the outermost edges to complete the reinforcement cage for the cantilever wall. In addition, Z-shaped rebars were used at the construction joints between cantilever wall to prevent horizontal shear failure caused by lateral loads. These rebars connected the bottom vertical rebars of the upper cantilever wall to the top vertical rebar of the lower wall, penetrating vertically across the joint to resist sliding along the interface during service. From floors 5 to 8, a modified construction sequence was applied. In these levels, the cantilever portions extended further than the terrace zones, and the cantilever strut walls of both wings met at the apex, introducing added complexity. Rather than constructing the terrace and cantilever zones simultaneously, which could have induced excessive bending, the team began construction from both the core and terrace side, finishing the terrace zone first before proceeding to the cantilever. To maintain proper timing between pours, the cantilever strut wall of each floor was poured only once the terrace zone of the next floor was nearly completed. Because the cantilever walls of both wings merged in this area, a single large shoring system was installed to support all 4 levels. Only the formwork panels for each floor were added separately. For the joining of inclined walls, the main rebars were adjusted in length and bent diagonally across the junction, splicing horizontal bars of one wall into the other, ensuring full structural integration along the slop joint. From floors 9 to 10, another adjusted sequence was used. This level rested atop the cantilever strut walls rather than forming part of them. The cantilever section at this level were the longest and hence subject to the high slots. Given the prior sequence, the complex rebar geometry at the inclined surfaces, and the need for extended curing time to prevent deflection, the 9th and 10th floor were constructed in a staggered manner. While the 8th floor cantilever was being cast, the middle section of the 9th floor cantilever and the 10th floor terrace zone were also under construction to maintain structure balance. One of the key challenges with Sluishuis cantilever system was that, while structurally sound, a natural downward deflection was unavoidable due to its size. Structure analysis predicted that by the time the tips of the 9th and 10th floor cantilever were completed, they would have deflected approximately 130 mm. To address this, a pre-cambering strategy was implemented to offset expected deflection during construction. Specifically, each floor was constructed slightly higher than its design elevation, applying a small upward camber per floor to preemptively compensate for future sag. Because the formwork system used for Sluishuis featured adjustable jackbolt table form modules, the height could be finely tuned. With its 5.2 meter floor section contributing to the deflection, a camber of approximately 8.1 mm per section was introduced. By adjusting the screw-type jackbolts, workers could raise one side of each table form to achieve the required camber. The construction team followed the pre-calculated camber table developed during structure design, and adjusted the formwork on site using the jacking system. As a result, the finer deflection was almost entirely compensated with floor height completed within just a few millimeters of the intended elevation, even after long-term loading. Sluishuis successfully overcame numerous challenges posed by difficult environmental conditions, geotechnical constraints, and the structural complexity of its unconventional form by meticulously planning and executing a high intricate and simultaneous construction process, ultimately establishing itself as a remarkable architectural icon.